Welcome all to the second lecture on the series of advanced abrasive machining processes, and the lecture will be focused on honing, lapping and super finishing operations. I am Dr. Monish Mukhopadhyay of Mechanical Engineering Department, Meghnad Saha Institute of Technology. Till now we have seen the details of the grinding process. Now we shall proceed to a few other abrasive processes like honing, lapping, super finishing. We will start with the honing process. Now, introduction to the process. Currently in this particular lecture, we will initially deal with the honing process, introduction to honing, what is a hone, which is a honing tool, the manual and power stroking in the honing process, material removal mechanism in the process, how the mechanisms work, lubricants in honing process, or the cutting fluids that are used in honing process, and the application of the process in different sectors like automobile industry, where it is commonly used for manufacturing operations of different engine components. Now we can see the roughness which can be achievable, or the smoothness which is achievable by the different manufacturing processes, and in the previous class we have read about the grinding process, and if we identify that, or if we compare that with the honing process, we can see that the level of finishing achievable by this process is far more superior than that using grinding process. Now coming on to the process itself, honing is a final finishing operation conducted on a surface, typically an inside of a cylinder, such as of an automotive engine block. Abrasive stones are used to remove minute amount of material in order to tighten the tolerance on cylindricity. It applies a slight uniform pressure to a light abrasive that wipes over the entire surface. Honing is an abrading process for removing stock from metallic and non-metallic surfaces. It is used to correct local irregularities such as ovality, waviness of the axis, or non-parallelism of cylindrical features, and to develop a particular texture. Honing is the application of bonded abrasive stones to a surface. The abrasive particles, generally aluminium oxide or silicon carbide, are held by proper bond in form of sticks, as you have read for the grinding process. Honing is employed for grinding internal or external surfaces. Mostly honing is done on internal surfaces or hones such as automobile cylinders. However, it cannot correct hole location or perpendicularity. Surface finish of around 0.05 micron can be achieved, that is the average surface roughness. The hone rotates at around 0.5 to 2.5 meter per second speed and reciprocates at 0.2 to 0.5 meter per second. The hole to be honed is flooded with a lubricant like paraffin, while the honing sticks are removing material. A honing machine rotates and reciprocates the hone inside hole being finished. Let us see a video to understand the working of the honing process. It is the honing tool which is being inserted into the cylinder inside of the cylinder for finishing. display inside of the cylinder. As you know, the process requires high surface finish. This is the control of the CNC of the honing machine. Now the tool is being inserted in the next hole, the cylinder block, and as you can see, while being inserted, the tool expands after being inserted, which lets the abrasive shoe around the honing tool to interact with the hole, and due to its high rotating speed and the cutting fluid which is being provided, we get a very smooth finish. Now coming on to the honing stones. Honing stones can be like two type of honing stones are generally used in the honing processes. Honing stone having conventional carborundum or silicon carbide abrasive grits, or they may contain boron nitrate, that is CBN, or diamond abrasive wheels. Now, honing stones with corundum or silicon carbide abrasive grits. The honing tools with conventional abrasive grains receive their desired form through mechanical material removal. Since narrow honing stones adjust themselves to the workpiece to be processed very quickly during their first use, a separate profiling process is rarely necessary. Only when machining holes with very small diameters, the honing tool must be rounded with leveling sleeves made of hardened steel. Honing stones which are either new or blunted through use must be resharpened. This sharpening process can be done in two ways during machining. First, it is possible to increase the contact pressure of the honing stone, which causes the grains to splinter or break away. In addition, a sharpening effect can be achieved by increasing the oscillation speed. Now, honing stones with boron nitrate, that is cubic boron nitrate, and diamond. In contrary to conventional honing tools, CBN or diamond honing stones must be adapted to the form of the workpiece prior to use. For the honing of hones, for example, the tools are ground to the dimension of the hole in a pre-tension state on an external grinding machine with silicon carbide or precious corundum grinding wheels. After this profiling process, honing tools have no cutting efficiency, so that a downstream sharpening process is required. For this purpose, moist, loose silicon grains are dispersed between the workpiece and the tool during the honing process. The resulting lapping process sets back the bond to the grains, which facilitates the tool's cutting ability. Another possibility is to use the moist, soft corundum stones. Both producers have in common that the selected grain size of both the loose silicon grains and the corundum stone is smaller than the grains of CBN or diamond honing stone to be sharpened, so that only the bond is removed. Not only stones, but honing oil plays a very critical role in enhancing the cutting ability of the process. That is very clear, as we have studied the effect of cutting fluids in our previous lecture. Now, honing oil are a critical part of the honing operation. Additional to the lubrication, the honing oil contributes by cooling the workpiece and honing tool, as well as by flushing the swaths away from the cutting process. If that is not done, we may get undesired surface roughness in the process. By keeping the process at the right temperature, both cylinder liner and the stone can be preserved to ensure quality and lower production cost. The most common fluid used is mineral oil. This is due to the high viscosity and high flash point. Another benefit of the oil is that it does not irritate the skin of the machine operators. Now coming on to features of honing technology. There are certain features which are listed over here. We will be talking about them one by one. The first one is high machining accuracy. There are some small and medium sized through holes made by the process and their cylindricity is within 1 micron. The roundness of some parts with uneven wall thickness is 2 microns, such as connecting rods. The roundness can also reach about 5 micron for large holes. It is possible that straightness can reach within 0.01 mm to 1 meter if there are not ring grooves or radial holes. The accuracy of honing is higher than that of grinding. Because of the bearing support of the grinding wheel is located outside the honed hole when grinding. It is a reason for the deviation. The grinding accuracy is worse for small hole precision. Generally, honing can only improve the shape accuracy of the workpiece. If we want to improve the position accuracy of the workpiece, we should take some necessary alternate measures. The second point is it is able to achieve a very good surface finish and surface quality. It is good for storage, lubricating oil and maintenance of oil film for cross mesh surface. There is a higher surface support rate, that is the ratio of actual contact area and a matching area between the hole and the shaft, and it can bear the larger load and has good wear resistant. Improving the product service life. Honing speed is low and the surface of honing stone in contact with the hole is also low. So the average grinding pressure of each abrasive grain is small and the heat of the workpiece generated is also very small. There is no thermal damage and metamorphic of the workpiece and the deformation is small. There are almost no sanding and extrusion hard layer on the honing surface, which results in lesser ploughing actions. The third is wide processing range. Many processes like various cylindrical holes, through holes, discontinuity holes on axial and radial, keyway holes, pline holes, blind holes, multiple step holes, etc. can be made using this process. In addition, a special honing head can also process conical holes, elliptical holes and other different holes like form processing. Cylindrical honing tools can hone a cylinder, but the removal margin is far less than that of inner cylindrical honing. However, honing can process almost any material, especially the diamond and CBN abrasive wheel used or the grits when used, which further expands the application of honing and greatly improves the honing efficiency. Now coming on to small machining margins. Honing is one of the least removal margin processing method in order to achieve the required accuracy of drawings. In a honing process, honing tool takes the workpiece as the guide to cut the surplus allowance of the workpiece and achieve the required accuracy of the workpiece. When honing, the tools first hone the parts of the workpiece with much allowance, then gradually hone the parts of the workpiece with less allowance. Coming on to strong ability of holes rectification. Due to some shortcomings of the process method in technology, some processing defects may appear or will appear in the process, such as out of round, mouth of a bond turbo hole, uh, small size, drum size, uh, errors that may creep in different tapered honing processes. Like honing can greatly improve the dimensional accuracy, roundness, straightness, cylindricity, and surface roughness of the hole by removing the least machining allowance. Uh, as the penetration or the penetration depth or the infeed of the honing is very less, much smaller than the grinding process, so even if some error occurs in the hole, then also due to minute removal of the material, the rectification is very much possible, or a very viable option for this honing technology. Now these are the input variables of the process. The system has some input variables like machine, its type, property, workpiece, its geometry, pre-machining what it has been done, the property of the material, then honing tools, the type, the configuration of the tool, cooling lubricant, which type of lubricant, what is the material, how it is going to chemically react with the things, then the contact pressure or flow rate of the cooling lubricant. The variables are axial speed, that is the oscillation, circumferential speed, stroke frequency, stroke length, contact pressure, contact length, etc. Then honing process, the parameters for identification of the process are cutting forces, that is the machinability. We are studying the machinability of the honing process. The cutting forces might be considered. Then the cutting power required may be considered to judge the overall performance of the cutting process. Then the wear of the tool might be an indicator of the honing process. The temperature rise which it is seeing, the process length, the duration which is taking. Now there are some disturbances which might creep in, like circular movement of the tilt or vibration, which may result into damage of the surface or inaccuracies. Like results may be cylindricity, roundness, surface quality, influence of the surface layer damage, tool wear might be a result, then cooling lubricant contamination, change of state might also be a result, like what is the state of the coolant after the process, that might describe the process as a whole. The presented system quantities represents most frequent fixed process variables that include the machine with its performance data, material rigidity and dynamic behavior, the workpiece with its property, geometry and state as determined by design requirements, condition imposed by the workpiece material, and the type, the quality of remachining. The honing tool with its geometry, precision and honing stone design, the lubrication system with its type, viscosities and concentration of the cooling lubricant and arrangement of the supply nozzles. The variables determine the possible system mechanics and kinematics of the process. The kinematics results from the superposition of two movements. Axial movement comprising the axial movement of both the tool and the workpiece, and rotation of the workpiece or tool in the machining of cylindrical surfaces or transverse movements in machining of level surfaces. If the kinematics is given, the mechanics of the machining is determined by the process variables like the contact pressure, pressure and quantity of the cooling lubricant, and the results as described earlier may be assessed on the basis of the different parameters listed over here. Next, coming on to the method of honing. There are two broad categories of the honing process, like based on the method of the honing that has been performed: manual stroking and power stroking. Normally, manual stroking methods are used for never tolerances are requiring is very high, or you need precise tolerances. Other thing is that you can do some of the things that you can go for is experienced people will be there in the staff, or experienced staff will be able to process the stroking or perform the stroking with it without proper jigs and fixtures, or by holding the workpiece in their hands. Let us see an example of the manual stroking method. A different workpiece, the internal surface of the workpiece are being honed by the operator is holding the workpiece material in his hand and performing the honing operation. Now another method is power stroke. In power stroke, the machine and the workpiece are loaded on the machine itself, and the auto feed is given to the machine. It helps in better control of the output process or the finish of the tool. So the surface roughness or the surface quality which we obtain using power stroking method is comparatively much better compared to manual stroking methods. Let us see a video to understand the power stroking method. And this is the workpiece holder. If a workpiece is loaded in this is the tool, and with the power stroking, this is the mechanism. With the power stroking, the workpiece is being inserted and coming out of the hole by the engine power itself. So the performance from this method is much higher compared to the manual stroking method. Now next will be types of honing machines according to their orientation. Now it can be divided into two different parts, that is vertical honing machine and horizontal honing machine. Vertical honing machine, in this type of machining process, the tool as well as the workpiece is held vertically. These machines are available in more spindle types. The workpiece is stable and the tool reciprocates. Fixtures are present to hold the workpiece in correct position. Hydraulic drives are present in modern machineries to control the tool and the workpiece. Vertical type of honing machines are generally suitable for shorter jobs. These machines are widely used when compared to that of horizontal honing machine. Let us see an example of a vertical honing machine. See the workpiece is being is the tool inserted onto the cylindrical block, and the machining is being performed. Now, horizontal honing machine. Longer jobs are machined with the help of these machines. These machines carry a horizontal spindle on which honing tool is mounted. On some machines, the workpiece is mounted on the table and is reciprocated to and fro. The hone rotates about its own axis and also slightly oscillates. This oscillation is controlled mechanically or hydraulically. In some cases, the honing tool is mounted on the travelling head and is rotated as well as reciprocated. The workpiece is held in the horizontal position and rotates about its own axis. The type of the machine is meant for very longer jobs. Correct machining sizes are checked with the help of gauges. There are some machines having more than one spindles. Let us see an example of horizontal honing. And this is the table area. There is a shaft which is being honed. Very long shafts can be honed using this horizontal honing process. The shaft is being fed into the honing tool, and this is the feeding mechanism. This is the honing tool, this is the honing tool which is being fed into the hones, into the workpiece. Now next topic is advantage and disadvantage of honing process. Now variety of materials can be chosen in this process. Then good surface finish, or very good surface finish rather, may be obtained from the honing process. And disadvantage, the equipment cost is quite high, especially for the horizontal honing processes, and tool wear is quite high, as we know the controlled machining operations are being performed, and the grit dislodgement rate of the process is quite high, so the tool wear is obviously high. Now coming on to applications of honing technology. This honing technology find a wide range of application around automobile manufacturing, oil pump, nozzle industry, gear inner bore, supercharged parts. We'll be seeing them, also discussing about them one by one. Now in automobile industry, advanced precision hole processing technology is widely used in automobile and parts of manufacturing industry. Typical applications include engine cylinder block, cylinder sleeve, connecting rods, gear, oil pump nozzle, brake pump, brake drum, hydraulic cylinder, steering gear, superchargers, etc. It is widely used in the automobile manufacturing sector. Now in oil pump nozzle industry, honing machines developed for plungers in oil pump nozzle industry. It is used as the removal rate is very low, the surface finish is very low, and the surface roughness which it can produce, that is also very good. It is expected that to have produced a surface roughness of about 3 microns or so. In gear bore industry, nowadays honing technology is widely used for automobile gears such as planetary gear, sun gear, double gear, etc. In supercharger parts, the electroplated diamond abrasive sleeve can be used as honing tool with a multi-vertical axis structure, complete as a series of processes such as rough process, semi-finished process, finish process, and deburring in the cycle. The multi-station turntable can realize the automation of the process and improve the work efficiency in supercharger parts manufacturing. The next technology we will be talking about is next topic we will be discussing is lapping. Now lapping is also an abrasive machining process. Lapping is a mainly room-bound process with geometrically undefined cutting edges. It is a production and finishing process, respectively defined as chipping with loose grains distributed in fluid or paste, which are guided with a usually shaped transferring counterpart featuring ideally undirect cutting paths of the individual grains. The ultra precision machining method of lapping is followed according to the desired surface quality by the polishing process. In polishing, the components are pre-lapped in order to achieve high material removal while maintaining a good surface quality and dimension and form tolerance. Polishing is then performed in order to create highest surface quality, including a mirror finish surface. Lap surfaces exhibit almost exclusively undirected processing traces, a semi-gloss appearance, and when under strain are distinguished by little wear. Surfaces to be lapped are usually flat. If the workpieces have different geometrical shapes, correspondingly modification methods variation must be applied. From an economic perspective, these are not always reasonable choice of application. Given high demands of the quality of the workpiece, however, flat or cylindrical lapping has proved competitive in comparison to ultra precision turning, precision grinding or honing. So they are being employed nowadays. Often it is the only option to achieve the quality requirements needed. The following materials can be processed by lapping: metals, ceramics, glasses, natural materials like marble, granite, basalt, any kind of gems, plastics, materials used in semiconductor technology, as well as carbon, graphite, and even diamond. Geometrically complex components with little form stability can be embedded in a supporting mass, thus expanding the area of application of lapping method. Now we shall see a video of the process of the lapping process in There is a lubricant oil which is being poured. The workpieces are inside the chambers, and with the relative interaction of this disc and the plates above, lapped surfaces are produced. Now, material removal in lapping. Lapping distinguishes itself from other machining methods in some characteristics, like most workpieces can be processed without being clamped or fixed in this process. Allowance of about 0.2 to 0.5 millimeter are economically machinable. Like precision and ultra precision machining can be executed in one operational step. Changeover times are very short. Then components of less than 1 millimeter or even 0.1 millimeter thickness can be machined. The highest surface and roughness requirement can be met using this process. The minimum heating effect prevents undesired thermal distortion, so the finished surface or the final surface is of high, very high quality. A consistent machining quality is guaranteed for composite materials. Lapped surface rarely exhibits tensile distortion or burr formation. It is possible to machine multiple workpieces in one operational step. This is the lapping plate, this is the workpiece, and the grains, the temporarily fixed grains, whenever they are in like in interaction with each other, very controlled amount of materials are being chipped from the workpiece surfaces. We'll be talking about this in a little later slide. Now, working of a lapping machine. Let us initially understand this by seeing the video. Then we shall proceed to the mechanism of material removal in this lapping process. There is the working of a lapping machine. They are the work pieces. This is the lapping disc. And with the relative interaction between this lap plate and the upper plate, lapping process is being conducted. Now the loose abrasive grains which are interacting with the workpiece surface. And after the completion of the process, the workpieces are being taken out. This is for the machining of the other side of the product. Lubricants are being sprayed. Now, speaking about mechanism of material removal, in lapping, the work surface rubs against the workpiece surface to be processed. Machining is achieved by means of insertion of lapping slurry, lapping grains and the fluid into the working gap between the machining disc and the workpiece. In the process, loose grains are added either continually or intermittently. The existent dependencies and interdependencies respectively are complex. Material removal occurs as a result of the effect of the grain rolling on the contact zone between workpiece and the machining disc surface, or grains temporarily fixed in the disc surface. The edge of the lapping grain insert themselves into the working material. The depth of insertion depends on the surface strain and material, usually between 5 to 10% of average grain diameter. Through the vortex developing in the fluid film, the lapping grains straighten themselves out and become engaged. Their edges, which are moving along cycloidal path, engage the surface. Through the repeated penetration of the grains into the workpiece surface, ductile materials are sharpened until fatigue and then successively removed. In the case of hard and brittle materials, however, micro cracks are induced on the surface of the workpiece, the interconnections of which leads to the breaking away of the particles. The surface receives its appearances through the overlapping of the crater-like traces of the total indentation from engaged grain edges. Groove-shaped processing traces suggesting of the material removal caused by the cutting process are not visibly recognizable. The material dependent hardening is associated with an embrittlement of the material and is indicated by an increased surface hardness. The properties of the lapping discs are determined by both geometrical factors and working material. When machining workpieces with larger surface, disc grooving is necessary in order to ensure that there is even supply of grains at all points in the lapping disc. The abrasive material mainly used in lapping processing are silicon carbide, Al2O3 that is alumina, boron carbide and increasingly diamond. The lapping disc produces a rotatory movement and serves as a carrier for the lapping slurry, workpieces and dressing rings. The rotational speed must be measured so the impressible high centrifugal forces are avoided. Otherwise, the grains might leave a scratch marks. Lapping disc is generally made of special fine-grained pearlite cast iron material or of hardened steel alloy. To understand this a little better, we can see there are some grains over here. Whenever the lapping plate and the workpiece are being moved, like they are moving in a circular pattern, these grains which are in between present in the slurry which is being poured, relative interaction takes place between the workpiece surface and the lapping plate, and as the lapping plates are generally of higher wear resistant material, material removal occurs due to the penetration of the grains into the workpiece surfaces. And after these are being penetrated, the ductile material undergoes shearing. As you can see, a permanent indentation is formed whenever the material is being removed from the workpiece surface. Also, for ductile materials, we achieve material removal by brittle fracture. Now, this is a surface, ACM of a surface obtained from the lapping process. Now, speaking about parameters of the lapping process, there are different parameters which affects the lapping results to quite an extent. Kinematic factors may be there like rotational speeds, dimensional accuracies or the dimensions of the lapping plates and all. Then configurations, carrier configurations of the plates. Then in lapping plates, material, type of material which are being used, slot configuration, geometries, evenness. Then inside slurry, the grain materials which are being used, which directly affects the surface roughness as well as the quality of the surface which is being generated. The grain size, the distribution, the carrier fluid, it obviously provides the slurry provides a higher fluidity to the plates, which results in better surface finish. The concentration of the slurry, the volume flow rate which is being adopted, the machine on which lapping process is being done, there the normal force, power consumption, oscillation behavior, thermal stability, etc. The workpieces which are being machined, the material of the workpiece, the geometry, thickness distribution, all of these factors contribute to the ultimate lapping results. Then in tool, plate evenness, plate wears, in workpiece, shape and dimension accuracy are to be controlled. Then in economy, removal rate cost, this shouldn't also be very high, otherwise the cost of the component will rise and the mechanical process may not find its application in the industry. Now coming on to advantages, disadvantages and application. In advantages, extreme accuracy of the dimensions, like very high surface finish may be obtainable. If we go to the first slide, you may remember that the accuracy level of the, or the second slide, accuracy level of the lapping process is superior than that of honing process. Correction of minor imperfection of shapes that can be achievable, refinement of surface finish, producing close fit between moving surfaces. As the surface finish is very high, so fit attainable is also better in case of lapping process. It does not require the use of holding devices, therefore no workpiece distortion occurs. Additionally, in normal lapping, less heat is generated than in most other finishing processes. To minimize the possibility of metallurgical changes to the machine parts. When both sides of flat workpieces are lapped simultaneously, on an extreme accuracy in flatness and parallelism and the relief of the inherent stresses can be achieved, as the final surface, the material from final surface is being removed. So the manufacturing surface defects which might have crept in due to the previous manufacturing operations are easily removed by this process. Then talking about the disadvantages or limitation of the process, it is an extremely slow process. The material removal, understandably so, the material removal is quite low, so the process is generally very slow. And it is an expensive process because the slurry, the cost of the grains, the slurry is high. Also, due to the high precision operation, the precision of the machine itself should be very high. Now, application of lapping process, some of them are listed over here, and they are not limited to be precise. It is used in ceramic machining, brittle material machining, glass machining, etc. Now, moving on to the final part of the lecture, that is super finishing. Super finishing is a process in which rotating workpiece is finished by a relatively soft stone with fine abrasive oscillating parallel to the workpiece surface. The stone typically oscillates at an amplitude of 1 to 4 mm and a frequency of 10 to 50 Hz, and it contacts the workpiece at light pressure, typically 0.1 to 0.2 megapascal. The super finishing process consists of mainly three phases. First, the cutting phase, which is characterized by high material removal due to the sharp cutting edges. Second, the transition phase, which is characterized by a decrease in material removal due to dulling and loading of the stone. And the third one, the final one, the finishing phase, in which dulling and loading results in only slight or no material removal. So we get a highly finished surface. In the subsequently super finishing process, the loading stone or the loaded stone contacts the rough surface of the next workpiece to initiate self-dressing or auto sharpening, as we have spoken about it in grinding processes in lecture 1 of the stone, providing sharp cutting edges, and three phrases described are repeated. In comparison with honing and lapping, super finishing exhibits higher finishing efficiency. The process was originally developed to eliminate brinell marks from the automobile wheel bearing surfaces that resulted from long distance shipping. When automobile wheels were blocked to prevent rolling during shipping, only a few of the rollers or balls in the wheel bearings supported the weight of the automobile. Shipping vibration caused the hardened roller or balls to press against the bearing component and form slight depressions, a process called brinelling. When the cars were put into service, the depression caused excessive noise. It was found that brinelling could be eliminated by removing the fuzz generated in the grinding of the load carrying surfaces of the bearing. The development of fuzz removing process led to the development of super finishing process, and in early 1934. The process of superfinishing was first conceived by D.A. Wallis of Chrysler Corporation. Let us see some videos for better understanding or how what type of surfaces may be generated using superfinishing. The workpieces which are being fed for superfinishing to be carried on. The workpieces are coming out after the process has been completed. Let us see another example of the process. As you can easily be able to identify the finish of this part where superfinishing process has been performed is much improved than the surface as it was before. You see the finished surface, it is gradually moving to this side. The feed is in this direction. Now, the key applications of this process. Superfinishing improves surface roughness and forms accuracy in the material. The material removal mechanism in superfinishing are considered to be similar to that in grinding and honing or lapping as well. The controlled removal of material using abrasive grits. As grinding and honing do, superfinishing produces an affected layer. In the superfinishing of hardened steel, the layer thickness is about 1 mm, which is about 7 times thinner than the layer produced in grinding. The specific energy is in the range of 50 to 700 joule per millimeter cube and is made up of cutting and sliding action. The specific energy due to cutting consists of chip formation and ploughing components. The ploughing component is dominant when material removal rate is low. When the material removal rate is high, the ratio of ploughing component to chip formation component is smaller. Now, the application of superfinishing can be found in bearing industries, automobile components like crankshafts, camshafts, transmission shafts, gear pistons, cam followers, rollers, etc. In medical devices, in materials for very precise fittings, etc. Application of superfinishing can be found in many places. Now this brings us to the end of lecture 2. Thank you all.